In this session, we'll solve problems on singly reinforced section, and the problem type which we'll consider is analysis type. Okay. Now, there can be two type of problem. One is analysis, another is design. Well, you can distinguish between these two problems by looking into the data which has been given. Generally, in analysis type, the cross section of beam will be given or will be provided. Also, you'll find the tension reinforcement AST is also given. Now, with the help of this data, you may be asked to compute the neutral axis depth. You may be asked to compute the ultimate moment of resistance of the beam, or it can be asked to compute the load, the beam of given span can carry. Main thing is, in analysis type, the cross section of beam as well as the reinforcement is provided. Now, based on this two data, further you will be asked to compute some related parameters related with this two value, that is cross section area as well as AST. Whereas in design problem, it is possible that the cross section will not be defined. Also, AST will not be given. So what we have to do in design, we have to design the cross section as well as AST such that the beam is singly reinforced. Okay, and whenever you are designing a singly reinforced beam, we had already discussed, you always go with the design of under reinforced section or a balanced section. We have to remember, whenever we need to determine the cross section of the beam and reinforcement in the beam, if we are designing a singly reinforced beam, we need to make it sure that you always design under reinforced or balanced section. So here you can see, in design, cross section as well as steel is not known. For the given load, we need to determine these two values. Whereas in analysis type of problem, cross section as well as AST is provided to you. Well, now let us solve this problem, which is analysis type, and we'll find why it is analysis type. Now the question is, a rectangular beam 230 mm wide and 460 mm effective depth is reinforced with 3 number 20 mm diameter bars. Find out the depth of neutral axis and specify the type of beam. Determine the factor moment of resistance also. The materials are M20 grade concrete and HYSD reinforcement of grade Fe415. So here you can see the cross section area is 230 mm wide, 460 mm deep is being provided. Also this AST, the tension reinforcement, is also provided. Okay. Now here what's been asked, to compute neutral axis, specify what type of beam it is, whether it's a balanced section, under reinforced section or over reinforced section. Now based upon the type of the section, you need to go with defining its moment resisting capacity, or what is the maximum moment the beam can resist. So it can be called as determine the ultimate moment of resistance or factor moment of resistance. Both means same. Okay. The material grade has been specified. Like for concrete, we have M20 grade concrete, and in case of steel bar, we have grade Fe415. Now further, there is an extension of the question saying if AST is revised to 5 numbers of 20 mm diameter, what we have to do? We have to compute the factored moment of resistance. So again, you need to compute the ultimate moment of resistance. So here this term factored moment of resistance and ultimate moment of resistance both means same. So let us solve this problem. Let us write down the data which has been given for the beam. So what data we have? We have width of the beam as 230 mm. We have effective depth. What is effective depth? It is measured from the top of the compression fiber to the centroid of the reinforcement. So this effective depth has been given as 460 mm. Okay, this is 460 mm. Now AST, what is the area of steel given? So this AST is 3 numbers of 20 diabars. Okay, so this is 3 numbers of 20 mm diabar. So AST will be 3 into pi by 4 into 20 square. So this becomes nearly 942 millimeter square. Okay, the grade of concrete is given. What is the grade of concrete? It is M20, so 20 Newton per mm square. Grade of steel is given. It is Fe415, so F5 will be 415 Newton per mm square. Now what we have to compute? For this data, what you need to do? You need to compute the neutral axis depth as well as factored moment of resistance, that is ultimate moment of resistance. And this two value you have to find when you have 3 numbers of 20 dia bar. Now the another part of the question is also there, where if this 3 bar has been replaced with 5 number of 20 dia bar, we have to compute mu. But first what we'll do, we'll compute the neutral axis depth as well as moment of resistance for 320 dia bar. So let us do that. Now in order to compute neutral axis depth, so this xu is your neutral axis depth. Okay, and this is your factored moment or moment of resistance. And let me write down ultimate moment of resistance mu. Now you have to remember, whenever we want to compute neutral axis depth, what we have to do? We have to equate compression force equal to tension force. Okay, so what is the compression force? See, average stress 0.36 FCK is the average stress, and area of concrete in compression. So if this is my neutral axis, so this is the area of concrete in compression, so this becomes B into XU. So if I substitute the value of FCK and B from here, we get total compression force as, you can compute this to get 1656 XU. Okay, and what will be the unit? It will be Newton, because FCK is in terms of Newton per mm square, B is in millimeter, and XU is also in millimeter. What about tension? It will be 0.87 Fy into AST. Now, why I have written 0.87 Fy AST? So we have to understand the stress in steel is considered as 0.87 Fy. So this is valid if section is under reinforced or balanced, because if section is under reinforced or balanced, my stress in steel can be 0.87 Fy. If it is not, then the stress in steel will be FST. Okay, so right now I have assumed the section to be under reinforced or balanced, so that's why here tension I have written 0.87 Fy AST. Fine. Now if I equate C equal to T, what we get? 1656 XU equal to 0.87 into 415 into AST is 942. So from here we get the value of XU as 205.4 millimeter. Okay, so this is the value of XU. Now when this value of XU as 205.4 is valid if section is under-reinforced or balanced. Now let us compute what is the balanced neutral axis depth, that is XU max for Fe415 steel. For Fe415 steel, the value of XU max is how much? 0.48 times effective depth D. Okay, XU max equal to 0.48 D. So how much you are going to get? So you substitute the value of D as 460, and if I do that, you will get this as 220.8 mm. Now it is clear that your XU is less than XU max. Here you can see this XU is less than XU max. It means that this assumption was true, that your steel is yielding. Okay, because in under reinforced section your steel starts yielding. So XU is less than XU max, that is the section is under reinforced. Okay, so you have an under reinforced section. Now if I want to compute moment of resistance, how you can compute moment of resistance? In order to compute moment of resistance, you have to do mu equal to C into lever arm, or it can be T into lever arm. What is the value of lever arm? Z. So Z will be D minus 0.42 x. So this is your lever arm. So you can compute this lever arm because you have the value of D, you have the value of XU, which is 220.8. You know what is compression force. So this is your compression force. So using that you can compute, or you can compute with tension force also. So I hope you can do this. Now we will solve the second part of the problem. In second part of the problem, we have 5 numbers of 20 mm dia bar instead of 320 dia bar. Now for this, we have to compute the moment of resistance. So the second part of the problem is this AST is becoming 5 into 5 by 4 into 20, 1570 millimeter square. Now the width of the beam is given to you. It is 230 millimeter. What is the effective depth of beam? The effective depth of beam is given as 460 mm. Grade of concrete was M20, that is 20 Newton per mm square. Grade of steel is Fe415, that is Fy is 415 Newton per mm square. Now what we have to do? We have to compute the moment of resistance, ultimate moment of resistance. For this, we need to compute neutral axis depth first. So let us compute neutral axis depth. Neutral axis, in order to compute neutral axis depth, what you do? You create C equal to T. Okay. Now what is compression force? Now if I want to know compression force, C equal to average stress 0.36 FCK into area of concrete in compression, that is G into XC. So I substitute the value of FCK, that is 20, width of beam as 230 mm. I get this value as 1656 XU Newton. Okay. Now what about tension T? So tension will be FST into AST. Now considering the reinforcement to yield. Now when the reinforcement yields, it yields when you have under reinforced section or balanced section. Okay, so if I do that, if I consider section to be under reinforced or balanced section, I can write stress in steel as 0.87 Fy into AST, area of steel. AST. Now here AST is 1570. If I substitute here this one, what tension force we get? We get 566,848.5. You can check that. We will equate C and T now. If we do that, is 1656 XU equal to 566,848.5, or we get XU as 342.3. This is the neutral axis depth which you are getting. What was the balanced neutral axis depth? XU max. We computed XU max as 220.8. So your balanced neutral axis depth is 220.8 mm. Here you can see your XU is what? Greater than XU max. Okay, so here what you can see, your XU is greater than XU max. So what you can interpret, you can say that the assumption that your steel is yielding is wrong, right? Because in over reinforced section your steel does not yield, so that assumption is wrong. So you have not got the correct value of XU as per this formula. So let us interpret. Now as you know XU is greater than XU max, we can say the section of beam is over reinforced. Now we know an over reinforced section is associated with compression failure. Okay. So here the over reinforced section is associated with compression failure, and we do not want this kind of compression failure. So what we have to do, we have to limit the movement of resistance of an over reinforced section. Now, whenever section of beam is over reinforced, we can compute this T has to be your FST into AST. Now how you can compute FST? FST can be computed if stress strain curve of reinforcement is okay. We can compute tension if stress strain curve of reinforcement is given. What we will do, we can compute the strain, and corresponding to that strain I can compute my FST, equate CNT, and we can get the value of XU. But in order to compute the strain, it requires some trial and error procedure, because what we need to do, we need to assume XU, and then we have to equate CNT. From there you will be getting the value of XU. Now you have to check the obtained value of XU with whatever you have assumed. Okay, so you have to keep on repeating this process. But right now we do not have the stress strain curve of reinforcement, as the question's not been given to you. And if you do not want a compression failure in your concrete, so for an over reinforced section, in order to avoid compression failure, what we'll do, we'll restrict my XU equal to XU. Okay, because I know you are going to get more moment of resistance, because in over reinforced section what happens, your XU is greater than XU max, but I do not want compression failure. So I would like to provide some underestimated moment of resistance for an over reinforced section so that I can avoid compression failure of the concrete in an over reinforced section. So here I have XU equal to XU max for an over reinforced section. What I have done, I am limiting the depth of over reinforced section to that of balanced. Okay. Now once I do this, XU equal to XU max, what we can do? I know my moment of resistance is what? My moment of resistance is C into Z, okay, compression force into Z, and tension into Z. Now, I will not be using T into Z. Why I will not be using T into Z? Because here T is FST into AST. And this FST we don't know for this over info section right now when I equate XU equal to XU max. Okay, so I'll suggest you have to use this formula C into Z because C is known to you and even Z. Z will be how much? Z will be D minus 0.42 XU. Now here as you can see XU equal to XU max. So how much XU you are going to have? It is 220.8 mm. Okay, so we have D minus 0.42 XU as the lever arm. And what is your XU? I have limited this XU to XU max, that is 220.8. So from here, what we get this lever arm, if you substitute the value, you are going to get the lever arm as 367.2 mm. Once you get this, what you do, you write down moment or MU. Compression force, what is compression force? It is 0.36 FCK B into XU. Lever arm is 367.2 mm, and let us do this computation. 0.36, grade of concrete is 20, width of the beam is 230, and XU just now we have limited it to 220.8. So 220.8 into 367.2. If I do this, what I get MU? You get this as 134.2 into 10 to the power of 6 Newton millimeter. So you have to be careful here. The unit is in Newton per millimeter square for stress, and for the cross section area or the dimension B and X is in millimeters. So you are going to get your moment of resistance in terms of Newton millimeter. So I can report this as 134.2 kilonewton meter. So this is the moment of resistance which can be reported for the second part of the beam when the reinforcement has been revised from 320 diabar to 520 diabar, and this we are getting by limiting my neutral axis depth to maximum neutral axis depth. Now if it is asked what would be the stress in steel corresponding to this particular movement, so that also you can do. So in order to do that, what is my tension in steel? It is FST into AST for over reinforced section. Now I want to find out the stress in steel corresponding to this moment of resistance. So I can do T into Z is how much? 134.2 into 10 to the power of 6 Newton millimeter, because FST is in Newton per millimeter square, AST is in millimeter square, Z is in millimeter. So if I do that, here it will be Newton millimeter. So I should make sure the moment of resistance should be also in Newton millimeter. So tension in steel, FST into AST. So AST was how much? AST was 1570. Z we had computed 367.2 equal to 134.2 into 10 to the power of 6. If you do this calculation, you will get the value of FST. and you'll find that this FST is less than 0.87 Fy. Okay, it simply means the over section stress in steel is not yielding. Okay, it has not reached the yield stress. So of course, your stress in steel will be less than 0.87 Fy. I hope it is clear. We'll consider another question. The question is, a singly reinforced beam 250 mm into 500 mm in section is reinforced with 4 bars of 16 mm diameter with a clear cover of 42 mm. Effective span of the beam is 6 meter. Assuming M20 concrete and Fe250 steel, determine the central service concentrated load P that can be carried by the beam in addition to its self weight. So here also you see the cross section has been given. Okay. Now the AST is also given. What we have to do for the beam having a span of 6 meter length, if the same section with this reinforcement is provided with M20 concrete and Fe250 steel, we need to determine what is the service concentrated load. So here you see we have to determine service concentrated load. So generally how you get ultimate load, you multiply partial factor of safety of load to the service load in order to get the ultimate load. Okay. Now this beam has to carry its own weight also. Now how you have to proceed in order to solve this question? The idea is what? Because of load, I need to compute the maximum moment. Okay, this maximum moment is because of load, and for the beam with this section and this reinforcement in the tension side, I can compute its ultimate moment capacity. Now, how your design can be safe if your maximum moment because of load is equal to your capacity, ultimate capacity of the beam. Now we have to understand, since we are equating maximum moment with ultimate capacity of the beam, this maximum moment when you compute, it should be related with the ultimate load. Okay, the maximum moment has to be computed with reference to ultimate load. Now once you compute maximum moment, this maximum moment has to be equated with the ultimate moment capacity of the beam in order to get this load, because when I compute maximum moment, we get an equation where this P will be associated with the maximum moment. So let us see how you can do it. So this is the beam. We have width of the beam which is given as 250 mm. Now here you see 500 mm in section. Now this 500 mm is not your effective depth. This is overall depth of the beam, that is D, capital D, 500 mm. We have a clear cover. Can you see? This is the clear cover to the reinforcement. This is given as 42 mm. Grade of concrete is M20, so FCK is 20 Newton per mm square. Grade of steel is Fe250, so yield strength of steel is 250 Newton per millimeter square. So how much is AST? It is 416 diabar. So 4 into pi by 4 into 16 square, which will give you nearly 804 millimeter square of steel. We'll be computing the effective depth from this geometry. So what will be your effective depth? Overall depth minus clear cover minus diameter of bar by 2. The same thing has been done. 500 is the overall depth of the beam minus 42 clear cover minus diameter of bar divided by 2. This will give me the effective depth. As I said, we have to compute the maximum moment because of the ultimate load. Okay, so what's been given? You have a beam of span 6 meter. Now, this is the beam in which you have the span of 6 meter. Now, in this beam, we have the self weight of the beam, which is acting as a UDL, and there is a concentrated load P, which is going to act on this. Now, whatever load which has been shown over here, these are your service load. How you will get ultimate load? You can get ultimate load by multiplying the partial factor of safety of load, which is 1.5 for your dead load as well as for your this concentrated load also. Okay, so I'll write down ultimate load on beam. So concentrated load, it will be 1.5 times P, and then we have this self weight. This will become 1.5 times weight due to dead load or self weight. Okay, so we need to understand whatever load has been applied here, it is a service load. When we compute maximum moment, that maximum moment should correspond to the ultimate load. Okay, so I have got this ultimate load on beam. One is concentrated load, that is 1.5 P. Another is self weight of this beam, which is 1.5 times self weight of the beam. Now we need to remember this, that in order to compute self weight of the beam, you should know what is the weight density of RCC. Weight density of RCC you have to consider as 25 kilonewton per meter cube. Whereas suppose if you want to know the weight density of plain cement concrete, you can take this value for your design consideration, 24 kilonewton per meter cube. Okay, so we have weight density of RCC as 25 kilonewton per meter cube. So we can compute what is WDL. Okay, WDL. What will be the self weight of the beam? Density of reinforcement concrete into cross section area. So what is the cross section area of this beam? Width of beam was 250 mm, that is 0.25 meter, into depth of the beam was how much? 500 mm, that is 0.5 meter. So here you see again the unit is 25 kilonewton per meter cube. So that's why the cross section area has been multiplied with unit meter, 0.25 meter and 0.5 meter. This is the cross section area. So we get self weight of this beam as kilonewton per meter. Okay. So what is the ultimate self weight? Ultimate self weight, let us represent this as W U dl. As we can see, it is 1.5 times WDL. So you multiply 1.5 into WDL, which we get as 4.688 kilonewton per meter. You please check this calculation. So ultimate self weight of this beam is 4.688 kilonewton per meter. Now design concentrated load. So ultimate concentrated load, let me mark this as PU. It is how much? 1.5 times. What will be the maximum bending moment because of this load? In this simply supported beam, the maximum moment will act at the midspan. Okay, so what will be the maximum moment because of this UDL? It will be W UDL ultimate dead load into L square divided by 8. Because of the UDL, we know the maximum moment at midspan, it is WL square by 8, whereas for concentrated load it is how much? Load into L by 4. So the ultimate load here it is 1.5 P. This is the ultimate load into length of the beam divided by 4. So this is the formula with which you can compute maximum moment. So I'll repeat, the maximum moment is going to act at the midspan. So at midspan, because of this UDL, what will be the moment? It will be W into L square by 8. So when I consider W, we have to consider the ultimate dead load, WUDL into L square by 8. So this is because of the UDL. For concentrated load, the moment at midspan, it will be how much? P into L by 4. Now we have to consider the ultimate load. So 1.5 P has been considered as the load into L by 4. Now I can substitute the value of WUDL from here. Length of the beam is 6 meter. If I substitute this, if you substitute the value of WUDL, L for this expression, you are going to get 21.093 kilonewton meter plus, if I substitute the value of L as 6 meter, simplify this, you are going to get as 2.25 P, unit will be kilonewton meter. This is your maximum moment. As I said, this maximum moment has to be equated with the ultimate moment capacity of the beam. So next step is to compute ultimate moment capacity of the beam. Now to compute ultimate moment capacity of the beam, what we have to do? We have to compute neutral axis depth. Now to compute neutral axis depth, we do C equal to T. Okay. Now what is C? It is 0.36 FCK B XU. And what is T? Assuming the section to be under reinforced or balanced section, the steel will yield, so it will be 0.87 Fy AST. Now I'll substitute the value of FCK, B, Fy and AST. From here we are going to get the value of XU as 97.15 mm. Now in order to confirm whether the section is balanced or under reinforced, what we have to do? You have to compute the maximum neutral axis depth, which will be for Fe250 steel, it will be 0.53 times the effective depth D. Okay. Now when I do this computation, it will be 0.53 into 450. Now you can clearly see that your XU will be less than XU max. Okay, so if XU is less than XU max, it means section is under reinforced. So if section is under reinforced, it means that here the stress in steel, which is considered as 0.87 Fy, is correct. Okay. Now what will be the moment of resistance? The moment of resistance will be what? Either you can take C into lever arm or you can take T into lever arm. Let us consider C into lever arm. If I do that, it will be 0.36 FCK B into XU. What is lever arm? Lever arm will be D minus 0.42 XU. So we already know the value of XU. All the values are known. If we substitute here, we get ultimate moment of resistance as, so we can compute, it will be 71.56 kilonewton meter. Now what we'll do, we'll equate maximum moment with the ultimate moment capacity of the beam. This maximum moment is because of the load and this is the capacity of the beam. If I equate these both, you are going to get the value of P as, you can try this, 22.43 kilometer. This is the service load which can be applied safely on the given beam section of span 6 meter. Let us now solve a last question on analysis. Here we have a rectangular section of effective size 300 mm into 500 mm. Now when it's written effective, it means this 500 is the effective depth. Okay. So we have rectangular section of effective size 300 mm into 500 mm, which is used as a simply supported beam for an effective span of 7 meter. It's asked what maximum UDL can be allowed on the beam if maximum percentage of steel is provided only on the tension side. What do you mean by this statement? Only on the tension side, if it is provided, it's a singly reinforced section, maximum percentage of steel. Now always remember, maximum percentage of steel corresponds to balanced section. Okay, so maximum percentage of steel, this line, maximum percentage of steel, this corresponds to balanced section. And right now, so what we have to find? We have to find the maximum UDL that can be allowed if maximum percentage of steel is provided. Okay, and I have written maximum percentage of steel corresponds to what? Balanced section. And it's written on the tension side, it's a singly reinforced section. So what is the material? We have M20 grade concrete and Fe415 steel. Also, what we need to do, we need to find out the maximum percentage steel for this problem. So let us write down the data. What data we have? Width of the beam is 300 millimeter. Effective depth of the beam is 500 millimeter. Grade of concrete is 20 Newton per millimeter square. Then we have grade of steel is Fe415, that is Fy is 415 Newton per ounce square. Okay, now what we need to do, we need to determine the maximum UDL that can be allowed on the beam. Okay, so what is the maximum moment because of the UDL? Ultimate UDL into length square divided by 8, because we know if we have a simply supported beam, if in this beam if we have the ultimate load as W, the maximum moment will act at the midspan, which will be W L square by 8. This is my maximum moment. Okay, so if I substitute the value of length, I get maximum moment as 49 divided by 8 W kilonewton. Okay, now what is the moment carrying capacity of this beam? Now here you see the AST has not been given, but it has said maximum percentage of steel. And I am saying maximum percentage of steel corresponds to balanced section. Now for balanced section, can I compute mu lim, limiting moment of resistance? For balanced section, we know what is the limiting moment of resistance. For Fe415 grade steel, I know the formula is 0.138 FCK degree square. Now, if you don't remember the formula, don't worry. What you can do, you can still apply that formula equal to what? C into lever arm. Okay, what is C? 0.36 FC into B into XU max, because the cross section area is BXU. So instead of XU, you have to write down XU max, and lever arm is D minus 0.42 XU. So if you substitute the value of XU max, and what is XU max? For Fe415, it is 0. How much it is? 48 into D. Okay, so this is your XU max. So I can substitute here, and finally you're going to get this formula. So if I compute mu lim using this formula or this formula, we are going to get the answer as 207 kilonewton meter. 207 kilonewton meter. Now this is the moment carrying capacity of the balanced section, and what is the moment which is coming because of the ultimate UDL. It is 49 by 8 W. So I have to equate these both. If I equate these both, and maximum equal to mu, what we are going to get, we will get 49 by 8 W equal to 207, or W equal to 33.80 kilonewton per meter. So you please do the calculation and check whether this answer is right or not. So this is the ultimate UDL which you can apply. Now basically I would like to know what is the working load which is going to be applied on the beam. So I can write load carrying capacity in service condition or working condition. So load carrying capacity in service condition will be how much? W divided by 1.5. Because when I say what is ultimate load, what you do, you have to multiply the load factor, partial factor of safety of load, with the service load. So if I want service load, you have to divide the ultimate load by 1.5. And if I do this, I get W equal to how much? You get 22.53 kilonewton per meter. Now, this W is what? Dead load of the beam, that is self weight of the beam, plus imposed load of the beam. Okay, because in a beam you will be having self weight and imposed load. So this should be equal to how much? 22.53 kilonewton per meter. So what is the self weight of the beam? Weight density of RCC, which is 25 kilonewton per meter cube, into cross section area. Okay, in cross section area, what we have to do? Width of the beam 0.3 into depth of the beam, capital D. Now whatever D was there, that is small d, effective depth was 500. Okay, so 25 into 0.3 into D plus W in equal to 22.5. Now here I want to know this D. How you can compute this D? So this D is basically effective depth D, okay, plus clear cover plus diameter of the bar divided by 2. Now this C plus 5 by 2 is also called as effective cover. Okay. So what we'll do, assume effective cover as 50 mm, because we do not know what is the steel quantity, what is the diameter of the bar, I do not know. So I can assume effective cover as how much? 50 mm. So if I assume the effective cover as 50 mm, my D becomes how much? 500 plus 50, which is 550 mm. So here in this equation, 25 into 0.3 into overall depth of the beam, just now we have computed 550 mm, so 0.55 meter plus imposed load equal to 22.53. If I solve this, what we will get? We'll get imposed load as 18.41 kilonewton per meter. This is a service imposed load which can be applied on the beam. Okay. Now, in the second part of the question, we have to compute the maximum steel. We already know what is the neutral axis depth. Now, neutral axis depth is our maximum neutral axis depth because the section is balanced. Now, if I do C equal to T, so what will be C? For balanced section, it will be 0.36 FCK B into XU max. And what will be T? Since the balanced section still has reached its yield stress 0.8 87 Fy AST into liver arm. Liver arm is how much? B minus 0.42 XU. So here all the data is known. Now whatever steel here it is there, since it corresponds to limiting neutral axis depth or balanced neutral axis depth, this AST is AST. If I solve this by substituting value of FCK, B, Fy, D and XU max, we get AST as 1435.81 millimeter. So please check the calculation. I hope these three problems which we have discussed is clear to you.